When you click a mouse, that abstract human intent has to be instantly translated into physical electrical voltage pulsing across a motherboard. The translation from physical intent to digital execution is chaotic. The Linux operating system exists as the ultimate mediator to manage that chaos. Look at the structural model of Linux. It operates using a strict hierarchy of concentric rings. At the center is the raw physical hardware. Moving outward, we find the kernel, then the shell, and finally the user-facing applications on the outermost edge. Notice how this middle ring, the kernel, acts as the central command authority. It stands entirely between your unprivileged software and the critical physical components of your machine. The OS is a protective gatekeeper, trading direct hardware access for systemic safety and organized resource distribution. By forcing every application to ask for permission, the system prevents catastrophic conflicts. Looking closer at that single kernel ring reveals a densely packed engine room operating multiple autonomous subsystems simultaneously. This diagram outlines those core subsystems within the Linux kernel. We can see the primary management units right at the top, the process scheduler and the memory management unit. These two modules keep applications in line. The MMU ensures programs don't overwrite each other's data in RAM, while the process scheduler guarantees no single application hogs the CPU's processing time. Alongside them, the virtual file system manages physical storage, the networking subsystem handles data transmission, and the inter-process communication unit allows separate programs to synchronize and talk to one another. How an architect chooses to organize these specific subsystems in memory determines the machine's entire identity. The physical arrangement dictates a harsh engineering trade-off. The choice is whether to build an operating system that is blindingly fast but fragile, or highly stable but incredibly slow. To understand this trade-off, we have to look at the strict separation of power in computing. Privileged mode grants total hardware access to kernel operations, while unprivileged mode restricts standard user applications. This diagram illustrates the monolithic architecture. That red line represents the privilege boundary. In a monolithic design, the operating system places every core subsystem directly below that line. File systems, IPC, the scheduler, memory management, and device drivers are trapped together in kernel space. Because these components share the exact same memory space, they communicate instantly. There is zero friction between them, giving the monolithic design a significant performance advantage. However, that shared space creates a major vulnerability. There is absolutely no internal isolation. If a minor device driver, like the software controlling your printer, hits a bug and crashes, it doesn't fail in isolation. Because it has root privileges and shares memory with the scheduler, that tiny error can infect the entire grid and trigger a complete system panic. A monolithic architecture bets everything on speed and internal trust. It risks total system collapse to eliminate communication lag. The alternative is to design for survival through absolute decentralization. On the right, the microkernel structure radically changes the privilege boundary. It strips privilege space to the bare essentials. Only IPC, virtual memory, and scheduling remain below the red line. Everything else, like device drivers, is evicted, running as unprivileged applications in user space. This creates an immense stability benefit. If a device driver crashes now, it simply reboots in user space without touching the core system. But that stability comes with a severe performance tax. Because these components are separated by the privilege boundary, they must constantly transmit instructions back and forth using inter-process communication. Microkernels sacrifice raw speed to mathematically ensure that no single point of failure can ever bring down the core machine. Real-world engineering rarely commits entirely to theoretical extremes. This graphic shows the full spectrum of kernel designs. In the center is the hybrid kernel. By allowing the boundary line to step up and down, it keeps performance-heavy services in kernel space while pushing non-essential components to user space. At the very furthest extreme sits the exokernel, which removes almost all abstractions to give applications direct control over the hardware. Operating system design isn't about finding one perfect structure. It is about selecting the correct set of compromises for the hardware's specific purpose. This leaves a logistical problem. If unprivileged user applications are safely isolated above the red line, how do they actually instruct the physical hardware to do anything? The answer lies in system libraries. As outlined in this list, they act as mandatory, standardized translators between user software and kernel mechanics. For instance, glib packages commands specifically for C programs, while libpthread translates the complex requirements of multi-threaded applications. These libraries take raw application requests and format them into safe, heavily scrutinized system calls. Only then are they allowed to cross into kernel space. By providing a universal vocabulary, system libraries allow developers to write software without needing to manage the intricate, low-level mechanics of the kernel below. The architectural tension between speed and isolation does not stop at the operating system layer. It scales all the way up to web applications. Look at this diagram of a modern e-commerce app. Its layout is a direct mirror of OS design. This application is structured exactly like a monolithic kernel. It bundles the shop UI, catalog, and order services into one tightly coupled executable, sharing a single database. Because of this structure, the application enjoys the same high-speed internal communication as a monolithic kernel, and it suffers from the same vulnerability. If the discount service module encounters a memory error, the shared architecture means the entire digital storefront crashes offline. Whether you are managing microscopic silicon voltage on a motherboard or processing global shopping carts on a web server, you are bound by a permanent law of computing, the strict inverse relationship between the speed of tight coupling and the resilience of isolation.